this talk, I'll be focusing on the design of parallel systems using system area networks. The term system area network is one we've coined to mean a network that's been designed specifically for use in building large systems. I'll first talk about alternative architectures for parallel processing, then focus on distributed memory clusters. I'll talk about clustering with standard LANs, and then about the requirements for networks specifically designed to address the problems not solved by LAN-based computing clusters. And finally, I'll talk about the details and specific trade-offs we made in designing the ServerNet system area network. Today, we're seeing a growing need for scalable computing for a number of different types of applications. In the past, scalable computing has been used for transaction processing, but now we're seeing the move towards multimedia transactions, with voice and image included along with text in each transaction. There are many other examples, like data mining, decision support systems, video servers, and World Wide Web servers that involve massive amounts of data. This movement from processing-centric applications to data-centric applications will require new architectures that have been designed from the ground up to handle the huge data rates. New architectures need to handle high-bandwidth communications between the CPUs and to the I/O devices. There have traditionally been two different approaches to parallel systems design: shared memory multiprocessors, also known as SMP for symmetric multiprocessing, and distributed memory multiprocessing, also known as clustering. Symmetric multiprocessing has an advantage in the case of applications development, but it has a disadvantage in the roll-off of performance as the systems scale. If all the processors are connected through a single bus, the bandwidth of that bus can eventually limit the scalability, and there's no choice but going to a clustered design. At the University of Minnesota, they recently did an experiment where they ran some scientific applications, both on a 16-processor SMP and on a 16-processor cluster connected with FDDI. The results showed that the smaller problems ran better on the SMP, but the larger problems ran better on the cluster, sometimes by a factor of 2 or more. On the large problems, the poor performance in the cluster was caused by increased cache coherence overhead and increased memory contention. Relative performance is always application dependent, and there will continue to be a market for large shared memory multiprocessors in the future, especially for scientific applications. But there are many other applications that will not scale well and will benefit from clustering. Commercial applications often fall into this category because they're very cache intensive, and the cache coherence traffic can quickly saturate the memory bus of an SMP. Another advantage of distributed memory multiprocessing is better dependability, because each of the processors fails independently rather than having a single processor failure take down the entire cluster. Also, there's an ease of incremental upgrade in a distributed cluster, while it's very hard to add processors online with shared memory design. Also, it's easier to use commodity PC-based software and hardware in distributed systems. In fact, the steep price decline of PCs is fueling part of the renewed interest in clustered distributed systems. So while shared memory multiprocessors and cache-coherent distributed memory processors will continue to be important for some applications, I believe that distributed systems will be the dominant architecture for very large-scale systems in the future. This talk will concentrate on distributed systems and their interconnections, and this will apply to both workstation clusters and massively parallel machines. The design principles are based both on experience with commercial clusters and on academic clustering work, like the UC Berkeley Network of Workstations, or our NOW project. The early commercial work in clusters was pioneered by the tandem nonstop systems that were introduced in the mid-1970s and the digital VAX clusters introduced in the early 80s. There have been many other commercial distributed memory machines, like the Thinking Machines CM5, Intel Hypercubes, and the N-Cube machines. Much of the recent commercial work has been influenced by academic hypercube projects, beginning with the Caltech Cosmic Cube project in the mid-1980s. More recently, there have been several new clusters introduced, such as the IBM SP2, the Pyramid machine, NMOS transputer-based clusters, and clusters based on the Encore reflective memory technology. In some applications, clusters are now beginning to replace traditional supercomputers with large numbers of workstations connected through high-speed networks. This is a generic diagram that shows the basics of clustering as it's currently implemented in many of these systems. Here we see two multiprocessor systems. Each is a small shared memory multiprocessor with perhaps 2 or 4 processors each. These are connected to an I/O bus and then through a network interface card to a fast network that connects them to each other. The advantage of this type of cluster is that it can use standard hardware because the designs of the processor and memory subsystems are exactly the same as used in standard workstations or PCs. The disadvantage, though, is that the latency of transfers from one CPU across the network to another CPU is very long due to the software overhead involved. For instance, if one CPU wants to read or write a location in the memory on the remote CPU, it has to format a message and send it through the network. Then the message has to interrupt the CPU on the other side, cause a context switch on that side, and then the remote CPU performs the read operation and sends the result back through the reverse path and causes another interrupt on the requesting side. The time for interrupts, context switches, and remote software execution can completely dwarf the time actually spent sending a short message across the wire. In many cases, the overhead is made even worse because of the many software layers in the protocol stack, in a stack such as TCP/IP. The large software overhead makes it difficult not only to do reads and writes of remote memory, but it also makes it difficult to share any of the peripherals that are on the remote system. The software overhead both limits the maximum rate that data can be sent and consumes a large percentage of the CPU processing cycles when heavy traffic is being sent. Another problem with traditional clustering approach is that it's not possible to share connections to high-speed or high-cost controllers like ATM controllers. Also, the network used in traditional clusters have no built-in provision for fault tolerance, which is required when the clusters grow to very large numbers of nodes. A completely different approach to clustering is to use a network specifically designed for that purpose. That is what we call a system area network. The definition of a system area network is a network optimized for clustering and used for both interprocessor communications and I/O scaling. System area networks can be used for scaling either the processors or the I/O, and the network allows the sharing of I/O devices and will support I/O to I/O transfers. The length of each individual link in the system area network is optimized for use within a single super server, but it may extend to perhaps a couple hundred meters in distance. A system area network is different from a LAN because it has higher bandwidth and lower latency, but may have shorter length limits. Also, the system area network supports direct I/O attachment and has hardware reliability features to allow lighter weight software stacks. So in some sense, the system area network is really a cross between a LAN and an I/O bus. The programming model for the system area network must support the porting of existing I/O drivers and messaging protocols, but it does allow new protocols when that's beneficial for higher performance or reliability. In this diagram, we see that all the CPUs and the I/O devices are connected directly to the system area network. In this case, I've shown a fault-tolerant network, which is comprised of 2 independent X and Y connection fabrics. The network supports connections to standard network buses, such as PCI, to high-speed networks like ATM, and to LAN adapters for connecting to local client workstations, for instance. The adapters are fairly simple and don't require powerful processors on the interface cards because the system area network allows direct read and write of the registers on the peripheral chips. The adapters don't require much more hardware than just the peripheral interface chip along with a single chip adapter into the system area network. Notice that with this architecture, all the scaling of both I/O and CPUs can be done through expanding the number of connections to the system area network. So it's a single place to concentrate the requirements for scaling a network and a single place to concentrate the fault-tolerant requirements. for instance for hot plugging devices for online service of CPUs or peripherals. In designing such a network, there are a number of different requirements that the network itself has to fulfill. I'll talk about the requirements for the network first, and then talk about the specifics of different types of interconnects that could fulfill those requirements. The first requirement for such a network is scalability. The network has to scale, in some cases to hundreds of CPUs or thousands of I/O devices. Clearly, using a single bus instead of a network would not give the desired scalability because the bandwidth of that bus would eventually saturate. So in this diagram, we see that as the number of CPUs increases, the network bandwidth grows in a network design, while in a bus design, that bandwidth stays fixed and will eventually saturate. The other advantage of a network is that we can use point-to-point connections that are electrically easier to build. This eases the length restrictions and improves fault isolation in the network. Clearly, for scalability to work, not only the hardware has to scale, but we need scalable software as well. Shared nothing databases have been shown to have a linear scalability up to a large number of CPUs. For instance, in a recent benchmark of the nonstop SQL database, linear performance growth was shown through 112 CPUs on the Transaction Processing Council's TPCC benchmark. This is a key factor in scaling a system, to have scalable software that doesn't have bottlenecks. The second requirement for a system area network is high performance. Performance is not just measured in bandwidth, but also has to include latency as well. This diagram shows one way of conceptualizing the I/O performance in a system. We can think of this as a pipeline where we're trying to push data through the network, and the width of the narrowest channel determines the amount of data we can pump through. So we have some bandwidth limit for communications lines, for the I/O channel, for the memory, and for the CPU code. In most communications protocols, the CPU code is the performance bottleneck, so reducing the CPU code path length is one of the most important factors for improving I/O performance. The primary performance requirement for a system area network in terms of bandwidth is to keep up with the fastest I/O devices. At this point in time, bandwidth should be at least around 25 megabytes per second because the SCSI-2 fast and wide disk interfaces are now at 20 megabytes per second. If we need to attach disks to this type of interconnect, we need a network that can outperform the peripheral bus. Second, we need the latency to be on the order of about 10 microseconds for the hardware. Especially in commercial applications, there are a number of message transfers that are very short, and the performance of the system is severely degraded if the latency is not fairly low. Previous experience with tandem nonstop systems, specifically the Himalaya line, has shown that performance suffers if hardware latencies on the interprocessor bus are more than about 10 microseconds. Also, any interconnect used to read and write registers of peripheral chips must have latencies that are comparable with the memory latencies, preferably in the sub-10 microsecond range. The next important requirement for a system area network is cost. From the first diagram of a system area network, you'll remember that there are quite a few connections to the network. We can't afford to have an entire board full of logic required to interface each one of those peripherals to the network. That would affect both the cost and the system reliability. So one of the key requirements is to keep the network simple enough that it can be implemented in a way that we can have multiple ports on a single ASIC, or application-specific integrated circuit. Another ingredient to low cost is to have a network with few enough pins or low enough frequency pins that it can be sent directly across the backplane, across cables, or across fibers wherever required. Also, the complexity must be low enough that we can afford to attach low-cost peripherals to this network. The final important requirement for system area networks is reliability. As systems scale, the mean time to failure of those systems decreases linearly with the number of components in the system. So in this diagram, we see a typical massively parallel system and its mean time to failure in days versus the number of CPUs in that system. And as we can see, as we get into hundreds or perhaps thousands of CPUs in a system, the mean time to failure, just of the hardware itself, drops to only a couple of days, where if we design the system with no single point of failure, we increase the mean time to failure of the system by about 3 orders of magnitude, a factor of about 1,000. So designing the system with redundant connections in a way that we can tolerate single faults is very important if we plan to scale these systems to a large number of processors. So given the four basic requirements for a system area network, bandwidth, low latency, scalability, and low cost, we can examine the different alternatives for such a network and see if current open standards will satisfy those requirements, or if we need something more optimized for this environment. This diagram shows a comparison of a few standard networks versus these parameters. I don't have time for a complete case study of every possible network that might be compared in this arena. There are a number of recent networks that have been proposed to do some of the features of system area networks, including the Miracom MiraNet network and proprietary networks at Pyramid, Cray, IBM, and others. There are quite a number of other alternatives, but this comparison should give you a flavor of some of the important criteria for choosing a network for use as a system area network. The alternatives shown along the left side include fiber channel, ATM at two different speeds, then SCI, which is the Scalable Coherent Interface, and finally P1394, which is the Apple FireWire Serial Peripheral Bus. First, looking at fiber channel, it clearly has very high bandwidth and has high scalability, but if we look at the packet switching latency, it's fairly substantial due to the store and forward nature of most switches. A recent fiber channel switch was announced with a switch latency of 26 microseconds, and if these switches are cascaded, it's not difficult to exceed 100 microseconds between nodes. Also, cost is a factor in system area networks, and fiber channel to this point has been a fairly high-cost alternative. ATM has been one of the most popular networks proposed for clustering, but if we look at the requirements, first of all, the 155 megabit or OC3 ATM is the current standard, but its bandwidth is only about 18 megabytes and can't quite keep up with SCSI speeds. ATM has generally not been proposed as a disk interconnect, but only for messaging. The latencies can also be fairly substantial for ATM. A recent study at the University of California at Berkeley measured the latencies through standard ATM switches and found those latencies to be between 26 and 208 microseconds round trip per switch. Again, if these switches are cascaded, we're well beyond the realms that would be tolerated for a system area network. Also, the cost of ATM is fairly high. Of course, those costs will be coming down with higher volumes, but ATM requires a fairly large buffer memory to be used for holding the virtual circuit assignments on the ATM network. So even as the technology improvements are made, there will still be a fairly steep cost for the memory associated with each ATM switch and network interface. I won't go through the details of each of the other designs. Scalable Coherent Interface has high bandwidth and latency, but again there's some question of the cost. And many of the vendors with designs based on Scalable Coherent Interface are making their own modifications so that it's doubtful whether there will be a set of standard components that can be purchased which will be interchangeable. The 1394 standard is the only one when we were designing our system area network which met the cost goals, but unfortunately it didn't meet the other goals. Finally, none of the standard networks have been designed from scratch to support fault tolerance. The requirements for redundant paths, for fault detection, and for fault isolation are very difficult to add to standard network components. Now I'd like to talk about some of the specifics on the design of a system area network that's been designed specifically from the ground up to address the requirements I've just talked about. The network is called ServerNet, and here we see its major design goals. First, it needed to support multiple different types of architectures, including shared nothing databases, clusters of SMPs, and shared peripherals. The network was designed to support multiple operating systems, including the nonstop kernel, standard Unix, and Windows NT. And it was designed to support different fault-tolerant models, including hardware fault tolerance, software fault tolerance, and fault resilience. In our terminology, fault tolerance means continuous processing despite any single failure in the system, where fault-resilient systems may have longer downtime after a failure while the application is migrated to a surviving node. And the difference between hardware and software fault tolerance is in the recovery model. With software fault tolerance, such as in the tandem nonstop kernel, checkpoints are sent between process pairs to establish recovery points. If there's a failure in the system, recovery takes place from the last checkpoint to that processor. In contrast, hardware fault tolerance uses redundant hardware to execute the same code stream multiple times, and if a failure occurs, the other hardware masks the failure and takes over without skipping a beat. So hardware fault tolerance requires more redundant hardware, but can easily port standard applications, while software fault tolerance has better price performance, but requires more effort in porting applications. Finally, ServerNet has been designed to support everything from entry-level machines up to massively parallel machines. So the network can scale both to very large and down to very small applications, in contrast to massively parallel machines that are aimed only at the high end. In implementing the network, we decided to concentrate on the essentials and keep it as simple as possible while still solving the problem at hand. So we concentrated on the scalability, the performance, the cost, and the reliability, but decided against some specialized features which might have had marginal benefit. For instance, we decided against memory mapped I/O because we felt it was an inefficient programming model. With the speed of processors today, it's very inefficient to have the processor stalled for tens or hundreds of instruction times while waiting for a memory mapped read to return from a remote node, even if that takes only a few microseconds. So instead, we've adopted a pure DMA programming model where the CPU programs the DMA engine, then the hardware takes care of the transfer while the software can go off to do more useful work. We also decided against using virtual channels because that complicates the router design, and we found a simpler technique for avoiding deadlock. We've also not implemented any hardware retry because we realized we needed software retry for other types of errors anyway, and rather than doing it twice, we decided to keep the hardware as simple as possible. The hardware retry would have increased the reliability a small amount, but would have greatly increased the complexity and the number of gates in the design. Finally, we also decided not to use adaptive routing, but to have fixed routing paths between the components. The reason for that is that adaptive routing makes it very difficult to guarantee exactly when a message will arrive, because a message could wander along a number of different paths before reaching the destination. For fault tolerance, it's very important to have a bounded worst-case latency. Then the timeout counters can be set to a value where timeout errors always indicate a real hardware error and can't be confused with network congestion. Now I'll talk about the physical layer of ServerNet design. This diagram shows the connections between a pair of components communicating through ServerNet. The physical layer has just a total of 20 point-to-point connections, 10 signals in each direction. The cables themselves can be 30 meters maximum length, and shorter cables or backplane connections are used when that length isn't required. The first cables will be shielded twisted pair cables similar to SCSI cables, but later we will also have fiber optic interfaces that extend the distances into the kilometer range. The point-to-point connections give excellent fault containment and isolation and make it very simple for hot pluggable design for online service. Also, sending a clock along with the data and resynchronizing it at each end means that we don't need a global synchronous clock. That would be very difficult to implement in a network where there are a large number of distributed components. This diagram shows the basic packet format. There are two basic transaction types in ServerNet, a read transaction and a write transaction. The read sends a header, address, and CRC to the destination, and then receives a response with the header, a variable length data field, and a CRC. The write just sends the address and data and gets back an acknowledgement. One of the key features of a system area network is to be able to do both reads and writes so that we can have a programming model similar to a standard I/O bus. That way the processor can read and write registers on an I/O controller, for instance. We also use the read capability extensively in the message system to reduce the number of interrupts and context switches in cases where the protocol can benefit from both pushing data towards the destination and from pulling data from a remote memory location. The writes are acknowledged so hardware can be sure that the data was delivered to the destination node. Both reads and writes use hardware timeout counters to signal an interrupt if the transaction was not completed in time. The timeout counters are programmable and are typically set to a few milliseconds. The packet format includes a source and destination ID in every packet header. These are 20-bit IDs which can address up to about 1 million different nodes. We include them in every packet header so that when a packet gets to the destination node, the packet can be validated, and we can make sure that it came from a valid source and that it arrived at the destination where it was intended to be sent. In other types of networks that use relative addressing, a fault can cause a packet to be delivered to the wrong destination, and there may be no way to detect that the packet was misrouted. In the packet, we also have a bit that's used to select the path, either X or Y, that will be used to deliver the packet. So the support for fault tolerance is directly built into the network. To switch to an alternate path, all the software has to do is to flip that single bit in the header, and then the pre-configured alternate path will take the message from the source to the destination. The packet also includes a 4-byte address, which is a virtual I/O address that gets mapped to the physical address in each of the destination nodes. So in many cases, when a packet is sent to a CPU, for instance, this address is looked up in an address validation and translation table, which is similar to the function of a TLB and is used to convert this virtual I/O address into the physical page number within that node. The address validation table also includes access rights to make sure that the packet was allowed to either read or write that destination. The packet also includes a variable length data field with 0 to 64 data bytes. This data field was intentionally kept fairly short for fairness in the network. If we had allowed very long packets, then the maximum latency in the network would have been long because the high priority packet might be stuck behind a large number of long packets before it could be delivered. And finally, all the packets include a 32-bit CRC that covers the entire packet, including the header and the optional address and data fields. The CRC is checked at each router and destination in the network, and if a fault is detected, we can automatically determine exactly where the packet was corrupted. This diagram shows the port design for connecting between two ServerNet chips, shown on the left and the right of the diagram. As a packet is ready to be sent, it first goes into an encoder to transform the bytes of the packet into the 8-bit, 9-bit code, which is actually sent across the wires. Then it goes through the cable buffers or through the backplane buffers and is received at the receive register on the other side. At this point, it's still synchronous with the sender's clocks, so it goes through a synchronization FIFO to convert to the local clock regime. Then it goes through a 9-bit to 8-bit decoder to recover the data byte or the command and into an elastic FIFO. That elastic FIFO has 96 bytes in the first implementation, so it stores little more than a packet. If the output destination is available, it is sent directly from that FIFO to the output. If the output path is blocked for some reason, the packet will start accumulating in the elastic FIFO. At some point, it's in danger of overflowing, and a signal indicates that this port is busy and wants the sending port to stop sending data until it's ready to start receiving data again. So that busy symbol is injected into a symbol stream in the reverse path, and it's transmitted back to the sending chip, where it indicates to that chip that it should stop sending data and instead start sending fill symbols. Eventually, the busy port will be freed up, and the busy elastic FIFO sends a ready symbol back to the other chip, telling it to resume sending data. So this implements a fairly straightforward link-level flow control to stop the flow of data when the network is congested. This gives ServerNet the ability to guarantee data transfers even in the presence of heavily congested networks, and the network will never drop packets as long as the hardware is working properly. This is different from some other networks. In particular, ATM is not yet standardized on the link-level flow control, and many of the routers actually begin to drop packets as they get congested. ServerNet uses what is known as wormhole routing, as opposed to store and forward routing. Here we see an illustration of the difference. With wormhole routing, when the head of the packet arrives in the router, the first few bytes of the packet indicate the destination, and the packet immediately begins to flow towards that destination without waiting for the rest of the packet to arrive. But with store and forward routing, the entire packet must arrive before the router can begin to send the first bytes to the next router. The store and forward latency is directly related to the packet length. It can be a large component of latency even with relatively short packets. By using wormhole routing, the first generation of ServerNet routers has a routing delay of just about 300 nanoseconds per router. This is a diagram of the 6-port ServerNet router ASIC. We see on the left side there are 6 input ports with elastic FIFOs on the inputs. Then the packets go into a non-blocking crossbar switch to the 6 outputs. When a packet arrives on the input, its first few bytes go to a routing table, which determines the path through the router, and then once that path is established, the following bytes just follow it through the crossbar switch to the output. The routing table doesn't need to look up the full 20-bit destination ID. Depending on where the router is actually located in the routing topology, it either looks up the high order 10 bits or another 10 bits of the destination ID that's shifted farther down in the word. This multiplexing of address bits into the routing table address greatly reduces the amount of on-chip storage required. The router also includes hardware to disable selected paths for deadlock avoidance. I'll talk more about deadlock avoidance when I talk about the preferred topologies for the network. The router is physically implemented in a 240-pin quad flat pack, and it includes just over 100,000 gates plus the random access memory used to store the routing table. The routing tables themselves are initialized through the maintenance system through a scan path used to configure the network. The X and Y paths through the network are configured at power on or when a node is added or deleted from the network. The next of the key chips used to implement ServerNet is the processor interface ASIC. The processor interface is the box shown at the bottom of this diagram and provides all the paths between the CPU, main memory, and a pair of ServerNet ports. All traffic to main memory, including traffic from the local processor, flows through this chip. When we get an inbound packet on one of the ServerNet links, the AVT, or Address Validation and Translation Logic, looks up the destination address in a table that's actually maintained in main memory. If the packet came from a source node with rights to access that portion of main memory, it gets the physical address the packet is trying to access. The chip will either read or write that memory based on the request in the ServerNet packet. This AVT table then also serves as a scatter-gather mechanism because a transfer can be contiguous in the virtual address space of ServerNet but may be scattered in different physical pages in main memory. For processor-initiated transfers, there is also an engine called the BTE, or Block Transfer Engine, which is the basic DMA engine that can be used to initiate transfers either to or from ServerNet based on a linked list of descriptors in main memory. The processor creates that linked list of descriptors, then writes a single register in the processor interface chip. Then from that point on, the hardware either takes care of sending data from main memory to a ServerNet port, or sending read requests through the ServerNet and taking the responses and putting the data into main memory. This chip also includes interrupt logic to take interrupts, which are standard write packets in ServerNet, and queuing them in main memory. The interrupt packets contain all the data needed for the processor to service the interrupt, and eliminates the need for extra transfers to read status registers on the I/O controller. The final key ServerNet interface chip is the bus interface. This chip does transfers between a single ServerNet link and a standard 32-bit bus, such as a PCI, VME, or a microprocessor type bus. The idea of this chip is that we can have standard burst mode read and write transfers on the standard bus, shown at the bottom, and those are translated automatically by the chip into ServerNet transfers. So for instance, if we're doing a read on that 32-bit bus, the read is intercepted by the interface chip. It formats a read packet and sends that packet off to main memory somewhere across the network. The read data then comes back and is placed directly on the 32-bit bus by the interface chip, and the I/O controller that was doing the transfer just sees a slightly longer latency than it would have if the memory had been local to that 32-bit bus. Similarly, on the reverse side, transfers from ServerNet can be translated directly to commands on the 32-bit bus to be sent to peripheral controllers. Future bus interface chips may support other buses, may have more ServerNet ports, and may have new capabilities to be able to do prefetching and write behind to improve performance. In a typical system, we'll have several bus interface chips. Each of them can have one or more peripheral chips connected to them. These peripheral chips typically have their own DMA engines so that all of those DMAs can be going simultaneously to main memory through the network. Here we see the 3 major chips we've just talked about and how they can be used to construct a system. The processor interface is shown at the top, a number of router chips are shown in the middle, and the bus interface chips are shown at the bottom. The system can be configured, as I said before, in several fault-tolerant modes. In software fault-tolerant mode, each of the CPUs would be running a separate code stream and would be passing messages through the ServerNet interfaces. In hardware fault-tolerant mode, both of the CPUs are running the same code at the same time, and the memories are kept in sync with the same contents in both memories at all times. When we have inbound I/O, we still have to keep the memories consistent, so the routers have a special mode where incoming I/O packets are duplicated and sent to both memory interfaces simultaneously. Then the incoming packets update both memories at the same time. If we get a failure of one of the CPUs, the other one can take over since it has exactly the same context as the failed CPU. The diagram also shows several ServerNet cable connections that can extend ServerNet either to remote peripheral cabinets or to other CPUs. We also have slots for ServerNet I/O cards. These can be used for I/O peripherals, for instance for ATM controllers, for additional LAN controllers, or for more disk controllers. All the I/O slots are dual ported so that even if we have a failure of one of the entire X or Y fabrics, we still have access to all the I/O cards. The SCSI subsystem is implemented as a dual initiator SCSI so that we can lose one of the SCSI chips and still have access to all the disks. And if for some reason we lose an entire SCSI string, the mirrors are maintained on separate strings so that we can tolerate even a catastrophic failure of a whole SCSI subsystem. Throughout the ServerNet design, we've built in a number of features for fault tolerance. It's very difficult to design a network out of standard components and then try to add the fault-tolerant features in later. Fault tolerance requires detecting faults as they happen and containing those faults so that they don't propagate to the rest of the system. Here we see a simplified diagram of one of the systems with the processor interface chips at the top, bus interface at the bottom. The processor interface chips are duplicated for self-checking, and they may also connect to duplicated CPU chips so that if there's a failure of any CPU or processor interface, the two copies will disagree and comparators are used to detect the failure immediately. The diagram also shows the address validation and translation tables that are critical for containing faults in the I/O system. The AVT tables prevent these faults from corrupting large regions of main memory. Another key fault-tolerant feature is the router support for dual X and Y fabrics, and the router supports special duplex mode I/O, which we call the equalizer. That's the mode where the inbound I/O is sent to both sides to maintain both memories in synchronism. The router designs themselves also have a number of fault-tolerant features, including duplicate state machines, so that we can detect failures in the control logic of the routers. They also have special path disables to prevent deadlocks in the system. Each of the ServerNet port interfaces of the ASICs have a number of checkers. First of all, there's the 32-bit CRC checkers, which are one of the primary methods used to detect faults in the system. As a packet progresses from one source to a destination, the CRC is checked at each stage along the way, and if a fault occurs, we're able to isolate exactly which chip caused the fault, and we'll know exactly which chip to replace. We also have protocol checkers and link-level flow control, as well as the keep alive protocol, which is the way we detect when links are added or removed from the system. And the link-level protocol also prevents a failing chip from bottling up the network and having all the traffic behind it stop. The main method for a node to be notified of a problem in the network is through the transaction timeout counters. Every time a read or write transaction is sent through the network, as it's sent, a hardware counter is started. Then if the reply doesn't get back to that node before the timeout counter expires, an error signal causes an interrupt. Then the software can retry over that path, or after a few retries can retry over the alternate path. We also have source validation hardware at the end nodes so that we can detect a node that attempts to illegally access a node it doesn't have rights to access. There are a number of other fault-tolerant features which have been discovered through previous experience, both with tandem non-stop systems and tandem integrity systems. For instance, one is the stale packet problem. In a network, you can have a failure which causes a packet to be held up, and that packet can be suspended almost indefinitely while that part of the network is being repaired. The problem occurs after the repair happens. If the stale packet then shows up much later at the destination, But at that point, the packet is out of context and might be accepted and cause a system failure. So we have a way of sweeping old packets from the network, a special type of packet transaction which goes through and destroys any packets in progress to make sure the path has no stale packets when it's restored to operation after a failure. We've also put in other hardware features to detect packets delivered to the wrong destination, and we've put in special hardware for fault-tolerant verification. Each of the ASICs is designed with special fault injection points built in, so that later, when we're testing the system, we'll be able to inject faults in both the control and data logic while applications are running. This will be very important for verifying that both the hardware checkers and the software recovery code are working properly, and we'll be able to do much more fault injection than the previous systems were able to do. At the higher level, we've also worked on what's called the split brain problem for clustering. That's the problem where if all communications fails between two groups of processors, each group may think that it's the only one surviving, and if there are any devices that are shared between these groups, each group thinks that it's in charge, and there can be fights over the ownership of the peripherals, causing system failures. So we've developed some new processor regroup algorithms to avoid that type of problem. Another key problem to solve in any kind of network design is to make the network manageable. In ServerNet, we've designed a separate maintenance subsystem which takes care of automatic configuration of the network, automatic fault isolation, and allows either remote or local maintenance of the system. The same maintenance system includes scan access to all of the ASICs so that we will be able to determine their state and have access to non-volatile memories on each of the components to be able to determine the configuration. The maintenance system also has access to performance counters to determine how the network is operating, and it also controls fault injection capability that we were just talking about. The maintenance system is controlled through a service processor which runs on a 68360 microprocessor under the PSOS real-time operating system. The service processor controls the ServerNet configuration and reconfiguration, and it detects changes as components are added or removed from the system. It also takes care of automatically reassigning the ServerNet node IDs and maintaining a consistent view of the system as nodes are added or deleted. The configuration process makes sure that the system is not configured with deadlocks which would cause the system to lock up. The service processor controls and has access to the environmental sense and control circuitry, and it controls hardware diagnostics and has support for remote operations through local area network or wide area network connections to remote processors. Finally, the service processor also controls the system startup and processor boot in the tandem design systems. Now, given all of these components for building a system, the next question is what topologies should we select for configuring large systems? We're not restricted to a completely regular topology, but need to have some recommended configurations that can be used in most situations. There are a number of popular MPP topologies, including the ring, the mesh, the torus, hypercube, banyan, as well as trees and fat trees. One of the key characteristics of many of these networks is that they have loops that could cause deadlocks. Basically, a deadlock is caused in a wormhole routed network by a number of packets arriving at just the right moment at a set of routers, such that each packet is blocked by the tail of another packet, as shown in this diagram. Here, A, B, C, and D all arrive at about the same time, and they're all blocked by one of the other packets. This sort of deadlock can occur in a hypercube, a mesh, a ring, or a torus network, for instance. We can break these deadlocks through the routing algorithms to make sure that we don't allow all of the packets to route at the same time. For instance, we can use something called dimension order routing in a mesh network, which means that you always route, say, first in the x direction and then in the y direction. In this diagram, this would cause two of the routes to be illegal, and there would be no deadlocks. In a hypercube network, it gets a little bit more complicated, but as long as you restrict enough of the paths to eliminate the loops, the network can be made deadlock-free. The problem with just disabling certain corner turns in the network is that the links then become unevenly utilized. In this example, the arrows show the paths that are not allowed. So at the top, the link labeled cool link connects only to the top node, and there's no pass-through traffic allowed. While the link at the bottom, the hot link, is used for connection to the bottom node as well as for a number of pass-through paths from the other nodes. A network like a hypercube looks like a symmetric network, but in fact it can be fairly asymmetric once the routing algorithm has been designed to break the deadlocks. There have been other methods used for breaking deadlocks in wormhole-routed networks, and the most popular is the one suggested by Dali and Seitz, in which they add multiple virtual channels. As I said before, we are very intent on keeping the complexity of the network as low as possible, and adding multiple virtual channels would have both increased the complexity and the cost of the routers, because it would have added a large amount of buffering in each of the routers. So instead of using that method to break deadlocks, we instead decided to find optimal topologies which were inherently deadlock-free by not having routing loops. What we came up with is the use of building blocks using fully connected sets of routers. In this case, the main topology is based on the tetrahedron. So here we see a tetrahedron in 3 dimensions, which is basically a pyramid with all corners connected. This can also be drawn more simply in 2 dimensions, with all pairwise connections between all 4 routers. The advantage to this type of topology is that while it looks like there are loops in the network, in fact none of the indirect paths between routers are ever used, because there's always a much better direct path. So as long as we only use the best path between any pair of nodes, there are no loops in this network. This diagram shows a 4-processor system along with a corner of a tetrahedron, so this is in fact a 16-processor system. We see the 2 different colors which are used for the separate X and Y fabrics, and the tetrahedrons at the top. This network is deadlock-free, and it turns out to be a very efficient way of connecting a system with 16 CPUs. Now we can extend this type of network of tetrahedrons through a tree of tetrahedrons in a structure we're calling a fractahedron. So this is a fractal tetrahedron, where a fractal is, of course, a structure which shows similar properties when viewed at different scales. So here we see a very small tetrahedron at each corner connected to the next level tetrahedron, with 8 of them surrounding it, and then 8 of these larger assemblies around yet another larger tetrahedron. So this is kind of a snowflake structure, and it can be used to scale the system into a very large number of nodes. In this case, we have a way of connecting 1024 nodes through a maximum of 10 router hops. By the way, if this were a fault-tolerant network, the entire structure would be duplicated, and every dual-ported device would be connected to both of the fabrics. You may be familiar with the measure of network topology called the bisection bandwidth. This means that if we cut the network in half at its weakest point, what is the bandwidth from one side to the other? Notice that in the fractahedron, we have only 4 links connecting each half of the system, so it always has 4 links of bisection bandwidth no matter how we scale it. This gives a low-cost connection for a large number of nodes, but the bandwidth doesn't scale. If we have a more demanding application where the bandwidth needs to scale, we can make use of the other connections at each of the corners of the lower level tetrahedrons. So here is a diagram that shows what we call a fat fractahedron, which is a similar structure to the fat tree, but rather than having individual routers, we have a tetrahedron at each of the branching points. Here we show 64 nodes connected together, with each of the low-level tetrahedrons connected to 4 at the next level. In this case, we have a bisection bandwidth of 16, and if we went to yet another level of tetrahedron, then the bisection bandwidth would scale from 16 to 64. So the bandwidth in this network scales as the network grows. This is the basic structure, both the thin and the fat fractahedron, that we use to scale these systems to a large number of nodes. The software environment for ServerNet is very dependent on the particular operating system that's running. However, we won't have time in this presentation to go into the details of each of these different environments. Our philosophy has been to take the ServerNet specific code, for instance for configuring the network and maintaining the network, and to isolate that code in a service processor so that as we change operating systems, we don't need to report the code every time. The programming model, viewed from an operating system perspective, is fairly simple. Most operations simply require the operating system to construct a small data structure in main memory to specify the transfer. The software writes a memory mapped register in the processor interface chip to begin the transfer. ServerNet hardware then does the rest, with subsequent operating system involvement only for exception conditions. The data structures can be chained together to form more complex commands. Higher-level messaging and I/O drivers are then built on top of this simple data transfer operation. Interrupts indicating exceptions or command completion are also straightforward and have low overhead. All the information that a device driver would typically need to complete a command or service an interrupt is contained in the interrupt packet. The performance of ServerNet can be measured both in terms of latency and in bandwidth. Router latency is 320 nanoseconds per stage for the first stage and 280 nanoseconds for the other stages. In a typical large system, we may have 6 to 8 router delays, or perhaps a worst case in a very large system of about 12 router delays. So in general, we're usually below 3 microseconds of latency, even for fairly large systems. In the first implementation, the bandwidth of each link is 100 megabytes per second. That's 50 megabytes in each direction. Or if we remove the header overhead, that's about 40 megabytes in each direction. The first processor interface can simultaneously receive packets over both the Y and the X networks while sending over one or the other. So that's a total of 150 megabytes peak, or 120 megabytes if we subtract the headers. Future processor interfaces will add more ports and allow simultaneous send and receive over all the ports. The first bus interface is limited to around 20 megabytes per second because it can't do multiple outstanding requests, since it doesn't have prefetch capability. The next generation will have that prefetch capability and will be able to saturate the links. The second generation of ServerNet, which we'll be working on in the upcoming years, will increase the frequency of the individual links by about a factor of 4. We're currently running a number of simulations of large systems to determine the loaded performance, and we'll be able to determine how well we've met our design objectives in handling burst traffic through the networks. So ServerNet has been designed really from the ground up as one of the first system area networks. It's scalable from the low end to massively parallel systems. It supports several fault-tolerant modes, and it supports CPU to CPU, CPU to I/O, and I/O to I/O transfers. In the development of ServerNet, we've learned a lot of new lessons in the design of systems and the design of networks. I think the first important lesson was that designing a new network is nothing to be taken lightly. It requires a huge effort. We certainly had the desire to use a standard network, but once we decided that none would meet the requirements, a very large investment was required. Initially, ServerNet was designed primarily for use in building fault-tolerant systems, but as the development progressed, we realized that the fault-tolerant features were also very important in developing fast general-purpose clusters. The same features that make it fault-tolerant give the hardware the ability to guarantee in-order delivery of packets. And this means that lighter weight messaging protocols can be used because they do not need to reorder packets or to check for correct delivery. So for general-purpose clusters, we're developing a standard PCI ServerNet card. This can be used for connecting networks of workstations and clusters of PCs, and can be used to connect fault-tolerant machines to high-speed clients. Another important application area for ServerNet is embedded switching applications, where we've seen quite a bit of interest. Also, the new capabilities for sharing of peripherals and for low latency access to remote memory can open up novel solutions to other problems that couldn't be addressed at all with traditional LAN-based clusters. A final lesson we learned in the development of ServerNet is that it's clear that many technologies have places where they're strong and other places where they're not as strong. ATM is a terrific long-distance connection network and will have huge success in those areas, but it doesn't currently make a very good system area network. Similarly, ServerNet will be strong in system area networks where high reliability and high performance are required, but not where very long distance is a requirement. In summary, I believe that system area networks will succeed where other solutions falter. System area networks are required where there's a need to scale systems from very low end to massively parallel. They're needed where lower latency and higher bandwidth are needed than can be provided with a standard LAN. They're needed where high dependability of the network is required, and they're needed where you need not only connections between CPUs and I/O, but also where there's a requirement to support multimedia and bulk transfers. Increasingly in the future, these very large data transfers will require so much data to flow through the system that it will not be practical to take that data into the CPU's memory and back out again. And this any-to-any capability will be very important for allowing the I/O system to scale independently from the number of processors. So I believe that system area networks are an emerging new class of network that will be required for building the super servers of the future. I hope you've enjoyed the talk. Thank you for listening.